Hello everyone. So we now come to lecture 4, and what I thought of doing in this lecture is go back to the all three lectures before and then take some concepts from there and do some advanced problems. So these problems that I'm going to discuss in this lecture video, I have got it from a different textbook which is called Parker Smith. So Parker Smith Problems in Electrical Engineering. So volume 2, if you see from this textbook, I got some of the problems, and then not actually this particular Parker Smith book contains quite difficult problems, and from that I have chosen the easier ones, and then I'm going to discuss this today. My intention is to make you understand some more practical aspects of these transformers and teach you by going through these problems. So as usual, you have the question on your screen, so you can pause the video, you can read the question, understand the question, and if possible, you can also attempt to answer the question, and then later on you can compare the results with what I get. So, meanwhile, let me start answering this question. So let's look at the data that is given. So estimate the active cross section of a core of 30 ton one phase inductor. So there's no transformer here. This is just an inductor for a terminal voltage of 100 volts at 50 hertz. All right. The flux density should not exceed 1 Tesla. So at least that part I can write. B max should be 1 Webers per meter square, or nothing but 1 Tesla. The maximum flux density is given, and I have to find what is the area of cross section. And also number of turns are given. So N is equal to 30, and then the voltage is also given, terminal voltage. E is given as 100 volts. What about frequency? Yes, frequency is also given. Frequency is 50 hertz. So I think we have good information for this problem to find out the cross section of the core. And the core is square shaped. What is the suitable dimension? So that we can, I think this is SI1, that we can handle it later. So let's first use our EMF equation that we learned for transformer. It can be applied for inductor also. So the EMF induced is nothing but 4.44 into F into number of turns into B max into area of cross section. So this is our formula. So from this I can determine what is A. So A will be E. So E is 100 volts given here. So 100 divided by 4.44 into frequency is 50, number of turns is 30, and B maximum is 1. So let's use our calculator to calculate this. So I have 100 in the numerator and divided by 4.44 into frequency of 50 into number of turns is 30 into flux density is 1. So this is my area of cross section. So I'm getting 0.0150 meters square, or in other words, this is nothing but 150 centimeter square. So this is the area of cross section that is required. So if the core is square shaped, what is the suitable dimension? So this is, if it is square shaped, so then if S is the side of the square, so S square should be nothing but area. So therefore S is square root of 150 centimeter square. So that will be, so let's do square root of 150. 12.24. So should you take 12 or should you take 13? So always go for the higher area. So I can go 12.24. So this will be 13 centimeters. So if my cross section area is 13 centimeters, that will ensure slightly larger area. Therefore, that will ensure that my flux density will not exceed 1 Tesla. So the condition is the flux density should not exceed. So if I round it off to lower value, if I round it off to 12, then to compensate the reduction in A, so B will increase and the flux density will exceed the 1 Tesla. So therefore, you take round off to the higher value. So this is I think the solution to the first question. So based on this, let's continue and look at more problems. So here, calculate the core and window area. So again, I invite you to read the question and understand what is there in the question. And some of it you might find it something which we not discussed in the previous lectures. You find something new, but at least some part of it you can solve it yourself. So you can attempt it and you can compare your solution with mine. Meanwhile, let me write down what is given in the question. So I am attempting to solve this now. So area of cross, that is my answer, sorry. Calculate the core and window area. So that is what is required for a 1600 kVA. So like this. So I think V1 is given 6600 and V2 is given 440. So these are in volts. And then S is given, that is 1600 kilovolt ampere, the rating of the machine. Frequency is given, that is 50 hertz. So it helps if you write down all the given data, it helps. Core type power transformer. So what is the meaning of core type transformer? The windings are surrounding the core as we have discussed. So let me core type. So how does it look like? So the core is like this. And on this core, you have the windings. So although in the diagram I am showing separately the primary winding and secondary winding, both windings may be actually together. In fact, to draw it more accurately, this wire might be a little bit more thicker, so it might actually take this much area. So this is the entire winding like this. And here also it takes some more area. So when you are designing the transformer, it is always beneficial to not have this extra place here. So why this extra place? So you can actually reduce this length and make it more compact. So we are trying to minimize the length of the transformer. Also the cross section area. So we want to minimize the cross section area. Best area we want to use it as physically as possible. So that is what actually this question is about. So core and window area. So core area is this one. If I mark the cross section, this is the core area, and window area is actually this gap in between. Not this gap. This is the entire window area. So window area. So I want to minimize this window area. So here what you notice is that there is a windings are stacked on top of each other, turns are stacked on top of each other, and there is a current density limit. See what happens, this is made up of copper wire and it cannot handle a particular amount of current more than particular density of current. Let's look at the equation. Core type power transformer, assume maximum flux density of 1.2 Tesla. So B max is 1.2 Webers per meter square or Tesla. And maximum current density, so let's call it as Jm. This is the current density of 3 amperes per mm square. So this is current density. So I'm using capital J for it as a symbol. So induced voltage per turn is 30 volts. So let's write E per turn, TURN, is 30 volts. And window space factor is 0.3. So this window space factor is like what fraction of the window I'm using and what fraction I'm not using and all. Something like that. So we'll come to it. So this is the data given to us. At least let's first try and work out the, let me write the EMF equation. So what is the EMF equation? So EMF is nothing but 4.44 into frequency into number of turns into flux density into cross section area. So this is what we know. Now if I want to know EMF per turn, then I can just bring the n here and then I can just simply ignore this n or actually transfer this n to the other side. Then this is the EMF per turn, that is given 30 volts. So therefore I am able to now find, so F is also known, Bmax is also known, and this whole term is also known. So I can find area of cross section from this. So area of cross section will be E by N is 30 and divided by 4.44 and frequency is 50 and maximum flux density is 1.2 Tesla, that is allowed. So this will give me the area of cross section of the core. So let's do that calculation. So I have 30 divided by 4.44 multiplied by 50 multiplied by 1.2. So here I am getting 1126. So 0.1126 meter square, or this is nothing but 1126 centimeters square. So this is the area of the core. Now let's, once I have this area of the core, let's continue and work out the area of the window. So I have calculated this area of the core here. Now area of this gap I want to find out. So for that you just notice what is there inside this. So first I want to find out how many turns are there in the primary and how many turns are there in the secondary. So for that let's find out number of turns. So what is number of turns in the primary? That is nothing but the voltage per turn. So EMF per turn multiplied by number of turns is nothing but the voltage. So this is EMF per turn is 30 volts, that is given. So therefore to find that, what we have to do is nothing but V1 by EMF per turn. So what is the voltage 1? 6600. So 6600 divided by 30. So this will give me the number of turns in the primary. So primary winding has 220 turns. Now how many windings, how many turns are there in the secondary winding? So that is nothing but V2 by EMF per turn. So that is what is V2? $440 volts, that is given to us. So 440 divided by number of turns, that is voltage per turn, that is 30. So let's calculate that. 440 divided by 30. 14.667 turns. So this is approximately, you can take the higher value, that is 15 turns. Now when this, so this many turns are there, let us also calculate what is the full load current, I1 at full load. So for finding the full load current, you can divide S by V1. So what is S? S is the 1600 kVA divided by this one. So this is 1600 kVA divided by V1 is 6600 volts. So let's see, 1600 divided by 6600. So this is 0.242 kiloamperes. So this is nothing but 242.4 amperes. So this way I got the under full load conditions, what is the primary current based on the rating. Similarly, what is the secondary current under the full load conditions? So let's calculate that also. So this is 1600 kilovolt ampere divided by the secondary voltage, which is 440 volts. So this is going to be quite high number, I think, divided by 440. So again, this is in kiloamperes. So 3636.4 amperes. So these are the currents that are flowing in the system. Now the thing is, the based on, like, if this much current is flowing, then it will have, we have to now look at the current density actually. So if I once again look at the window, so this is the core of the transformer. I'm just drawing the inside part of it. So I'm just stacking like this. So these are the windings, so on. So let's say for simplicity's sake, let's say this side part is low voltage and this side part is high voltage. This side part is high voltage. So in the will the low voltage side and the high voltage side, if you look at it, the current that needs to be calculated carried in the low voltage side is larger, 3636. So through this wire, that much current has to flow. So obviously we'll use the wire with thicker cross section area and so on, like this. Now the current density is also known. So if I multiply, so the number of turns multiplied by the current each is carrying, and then if I divide by the density of the current, then I'll get the area. So see, for example, each one is carrying current of I amperes. So let's say each one is carrying current of I2 amperes here. I'm talking about the low voltage side. So I2 is carried and then multiplied by how many turns are there in the secondary? 15 turns are there. So of course I have drawn more, but it is only 15 turns. This much is the current, entire amperes is flowing. Now divided by, I can transfer 3 amperes in 1 mm square. So if I divide by, so 1 mm square, I can transfer 3 amperes of current. So therefore, if I want to transfer 3636 multiplied by 15, so this is ampere turns. This much current, if I want to transfer, how much is the area I require? Is what is the question. So I can just now calculate that by 3636 into 15 divided by 3. It's an issue of current density actually. So this 3 is a current density. So in other words, N2 I2 is the total ampere turns divided by J is the current density. This will give me the area required for the low voltage winding A2. So how much is this? So let's calculate 3636 multiplied by 15 turns and divided by current density of 3 amperes per mm square. So I am getting 18180 mm square. So this is so also look at the units. This is amperes, this is just a number, and this is amperes per mm square. So finally amperes will cancel, and this mm square will go into the numerator. So area I'll get it in mm square. So how to convert mm square into cm square? So 1 mm or 1 centimeter is 10 mm. So therefore if I square both sides, 1 square centimeter will be nothing but 100 mm square. So therefore if I divide this by 100, I'll get 181.8 centimeter square. So this is the area required by the low voltage winding. The same way, in the same place there is a high voltage winding also through going through that window. So actually high voltage winding will have a thin, less cross section area wire, because and it will have more turns. So that way, so it's just completing like this. So let's do that. So A1 is N1 I1 by J. So N1 is number of turns, that is 220 turns, and 242.4 is the current. So 220 into 242.4 divided by 3. How much is this? 220 into 242.4 divided by 3. So I'm getting 17776 mm square. So this is nothing but 177.76 centimeter square. So this is the area of the first winding. Now that I have these two areas, so I can find out the total area. And then there is this stacking factor, that is, sorry, window space factor. So maybe that is the effective utilization, because not only the wires, there will be insulation between each wire. So each and every wire has to be insulated. So some kind of plastic or paper material will be inserted. Similarly, the high voltage side and low voltage side also has to be this one, and then there will be some gap at the top and bottom and all these things. So to do all that, so total area required, area of window, is nothing but A1 plus A2, so divided by the window space factor. So that is given as 0.3. So let's do that. So this is 181.8 plus 177.76 divided by 0.3. So 181.8 plus 177.76 divided by 0.3. So I'm getting somewhere like 1198.5. So 1198.5, or I'll just approximate it to 1200 centimeter square. So this is the cross section area required for the this window. So finally I have two answers. So one answer is this area of the core. So this, from this area of the core, if I assume the core is to be square shape, so let me calculate the side of the core. Side of core. So this is nothing but square root of 1126. So that is 33.5. So let's assume to be 34 centimeters. So my dimension is something like the core will have 34 centimeters as the side. So if I have this inside like this, so by the way, how much is this length? So if I again consider this as square shape, so what is the square root of 1200? So square root of 1200 is again 34.6. So again I'll assume that to be 35. So I got, this one is 34 and this one is 35. So let's mark that. So this distance is 35 centimeters by 35 centimeters. Then additionally I require 34 centimeters for the core all the way on all sides. So this is the square cross section for the core, and the side is 34. And this, so ultimately we are now getting the dimensions of the transformer core. So this is how the calculations are done to design a transformer core. So I hope you have learned something from looking at this problem. Uh, so and the earlier problem also that we had solved. So let's see some more advanced level problems. Okay, so let's continue and look at the next problem, that is example 17. So again, this is a kind of peculiar problem, and it gives you a good understanding of the importance of choosing the proper core material. So look at the question, try to understand what is being asked in the question, and we'll work it out. So the ordinary steel material for the core of a transformer is replaced with silicon steel. So basically we are replacing the core. The ordinary steel can support maximum flux density of zero point 0.8 Tesla, whereas the silicon steel can support flux density of 1.2 Tesla. So as a result, what will be the advantage? Determine the percentage saving in the volume of the core and volume of the copper if total flux remains unchanged. All right. So looks like some kind of a confusing problem. So let's be safe by writing my equation, that is EMF equation. So in terms of flux density. Now the if N1 and E1 everything is there, so it will be like this. Now let's say this is the maximum flux density for steel. So ordinary steel. So I'll write it OS here, and area of cross section ordinary steel OS here, like this. Now if I once again see, this product is actually 5 max. So this is nothing but 4.44 F N1 into 5 max, and this should not change. So again if I write it 4.44 F N1, now I am replacing the core material. Therefore my flux density maximum for silicon steel SS, from ordinary steel to silicon steel. So my area of cross section should reduce uh, in order to maintain the same flux density of 5m. So this 5m is same. So now if I divide this, so finally I'll get flux density is nothing but, sorry, the total maximum flux is nothing but flux density of ordinary steel multiplied by area of ordinary steel, which is also equal to flux density of silicon steel multiplied by area of ordinary silicon steel. So that way. So if the product needs to be maintained. So if you see the ordinary steel flux density is 0.8. Therefore, my silicon steel flux density is 1.2. So it is like this. So therefore, what is the ratio? So ratio of silicon steel by area of cross section of ordinary steel will be 0.8 by 1.2, and that will be 0.8 divided by 1.2. I'll get 0.667. Or in other words, if I want to find out the percentage reduction in area of cross section. is nothing but, so it is 66% of that. So basically it is the, like this. So this one, area of ordinary steel. So this will become 33.3 percentage. So I can reduce the area of cross section by 33 point. So therefore, assuming that the length will be same, so therefore the volume of core material will reduce by 33.33%. So that is the benefit. Now let's come to copper. See, what is happening is the area. What is the ratio of the side? If you consider the core is square shape, then the side of ordinary steel, and okay, side with silicon steel and side with ordinary steel will be square root of the area, square root of silicon steel by square root of ordinary steel. So this will be square root of 1.2 divided by, or this will be reverse, this will be square root of 0.8 divided by square root of 1.2, that is equal to, so 0.8165. So this is the side. That means now, if, let me draw the cross section like this. This is the core, and let me choose a different color. So this is core with ordinary steel. Now this one is the core with silicon steel. Now I want to wind a copper wire around this. So if I wire a copper wire around this, so here the perimeter of this will be what is my is the one which I would say, as compared to the perimeter of this. So if I look at this one, the perimeter of this will be the amount of copper wire. So number of turns will be same. The more copper wire will be required if the core is bigger, and less copper wire is required if the core is smaller. So therefore, that is why I calculated this side. So this is this one. So with silicon steel, 0.8165 of copper wire is sufficient. So, or in other words, if I want to calculate saving in copper wire, so from 100, if I subtract 81.65, so that is 18.35% saving. So this is the benefit. If you take any transformer, if you replace the inefficient core by efficient core means the one which can handle more flux density, then it will going to be a better thing. So while designing a transformer, you should choose the materials which can support the maximum flux density. So therefore, I like to give you a small homework for the YouTube viewers. So search in Google, what is the best material for transformer core? So that means, in other words, you have to search, you have to go for find out Bmax for different materials. So some materials cannot support that much of flux density into that. So in a given cross section area, how much flux it can handle. So that the capability of the material to handle more flux will be useful, and that material can be can be there. So just go to Google search and find out, try to arrange in ascending order or descending order, whatever, materials with respect to the maximum flux density these materials can handle. And you will notice that the best material which can handle the maximum flux density will be what is normally used for design of transformers. And this problem that we discussed will help you understand the savings. Okay. So that is about this problem, example 17. So again, I should give the credit. This problem is taken from Parker Smith's Electrical Engineering Problems Volume 2 on the topic of transformers. All right, let's continue. So this is kind of my own problem. So consider the transformer connections given below. Determine the primary current, neglect the core losses and copper losses. So and may I also ask you to draw vector diagram. So just look at this problem and try to understand. So there is this load L2 and there is another load L3. So suddenly you notice that there are three windings. Will the transformer work with three windings? So of course you know the working principle, you know the concept. So whenever there is a voltage applied to a winding, it will generate the flux, and that flux will link with this coil and generate EMF E2, and the same flux will link with this coil and generate EMF E3, and the same flux will link with this coil and generate EMF E1. So the same transformer principle will work here also. Next, what happens is that the current, so here is I2 and here is I3. The I2 current will result in I2 dash current, and I3 current will result in a I3 dash current, and therefore I1 will be the sum of, so in this case I1 will be I0 plus I2 dash plus I3 dash. Whereas this I0 is neglected in this, neglect core losses and copper losses, this is not there. So we just have to find out I2 dash and I3 dash, add them to find the I1. Anyway, let's jump into the problem and solve it. So let's begin by finding what is I2. So first of all, the number of turns, by the way, consider the transformer connection below. The number of turns is not given, I'm sorry. So N1 equal to, let's say, 1000 turns. N2, let's say, is equal to 500 turns. That means it is stepping down, whereas N3 is 1200 turns. This is slightly stepping up. So this is the way it is defined. So given this, find out what is I1. So let's first begin by calculating what is I2 and I3. So what is I2? So here you see 800 watts at 0.8 power factor lagging and the E2. So first, for calculating I2, we need to calculate what is E2. So E2 will be E1 into N2 by N1. So the turns ratio between these two I will use it. So E1 is given 100 volts and N2 is 500 and N1 is 1000. So when I do this, so I'll get 50 volts as my E2. So two zeros will go here, one zero will go here, 50 volts will remain. And if I know 50 volts, now I can find I2. So I2 will be E2 50 volts. First is the, see what is P2? P2 is 800 watts. Cos of phi2 is also given, 0.8 power factor lagging. So from these two, I can find out P2 is nothing but E2 I2 cos of phi2. So therefore I2 is nothing but P2 by E2 into cos phi2. That is 800 divided by E2 is 50 volts and cos phi2 is 0.8 power factor. So let us see how much it is. So 800 divided by 50 into 0.8. So 20 amperes is the current. Now you also know 0.8 power factor lag will mean phi 2 will be minus 36.86 degrees because of the lagging power factor. So minus 36.86 degrees. This is with reference to E2. So this is I2. So now let's calculate E3. So what is E3? So there is a transformer action going on between these two also. Depending on the turns ratio of N1 and N3, EMF will be induced in E3. So that is what I want to find out. So N3 is 1200 and N1 is 1000. So therefore E1 into N3 by N1. So 100 volts will be multiplied by 1200 by 1000. So two zeros go here, and so finally I'll get 120 volts is my EMF of, it's a voltage of E3. So now that I have E3, I can find out P3 equal to E3 I3 cos of phi 3. So from this I can find out what is the value of I3. So what is the value of I3? So power P3 given in the diagram 500 watts at 0.9 power factor leading. So 500 watts divided by E3 is 120 volts and power factor is 0.9, and this power factor is leading. So 500 divided by 120 volts and power factor is 0.9. So this will give me 4.63 amperes. 4.63 amperes and the angle. So I need to know what is the cos inverse of 0.9. So cos inverse of 0.9 is equal to A cos 0.9. So this answer will come in radians. So this radians I will multiply by 180 and divide by pi to convert into degrees. That is 25.8 degrees. Now here I should use plus 25.8 degrees because the power factor is given to be leading in the question. So if the power factor is lagging, then it should be minus 25.8. This is all with respect to E3. So now I want to transfer. So let me show you the vector diagram, that is important. So here this is my V1, which is 100 volts. As a result of this, I get two voltages here. One is E2 and the other is E3. So E2 is 50 volts, whereas E3 is 120 volts as I recall. So that's why I draw E3 slightly larger. Now the currents, so the current I2 was 20 amperes. So let's say this is I2 equal to 20. I'm sorry, it should be lagging the E2. I2 equal to 20 amperes minus 36.86 with respect to E2. So this is 20 amperes and this is minus 36.86. On the other hand, the current I3 will be leading. So I3 equal to 4.63 amperes at an angle of plus 25.8 with respect to E3. So this angle. So this is phi 3 and this is phi 2. Now we transfer these two currents to the other side. So this is I3 dash, exactly 180 degrees opposite to that, and this is I2 dash, exactly 180 degrees opposite to that. So what is I2 dash? So I2 dash is nothing but I2 multiplied by N2 by N1. Similarly, I3 dash is nothing but I3 multiplied by N3 by N1. So the respective turns ratio I will be using it. So what is I2? 20, and what is N2? So if I again refer back 500, so this is 500 and N1 is 1000. So therefore what I get? So zeros will cancel out. This 0 will cancel out. 5 into 2 is 10 amperes. And the angle will be same, but now this time the angle will be with respect to V1 minus 36.86 with respect to V1. Similarly, I3 dash will be, what is the current I3? 4.63 amperes. This current will be multiplied by N3, that is 1200, and N1 is 1000. So this will be 4.63 multiplied by 1200 divided by 1000. 5.556 amperes. And the angle will be plus 25.8 degrees. This angle will not change. So finally now I can calculate I1. Strictly speaking, that is I0, that no load current, plus I2 dash plus I3 dash. So I could have always given this information about this in the question, but this is anyway going to 0. So I just have to add these two. So this plus this I have to do. That is 10 angle minus 36.87, this is, and plus 5.556 angle plus 25.8. So this is the addition I have to do to find my I1. So let's do that here. So I2 dash equal to 10 into exponent of I into minus 36.87 and divided by 180 multiplied by pi, not to forget the units. So this is the current, that is I2 dash, and then I3 dash is the current because of the third. So this is 4 point, I'm sorry, 5.56 and the exponent, and here the angle is 25.8. So I'm getting I3 dash also. So now finally I1 is nothing but I2 dash plus I3 dash. So I'm getting this current 13 minus J 3.58. This is I1. Now if I convert into polar form, so let me do that. Absolute value of I1 and angle of I1. So 13.48. So of course angle I want to convert into degrees. So into 180 by pi, we'll convert the angle into degrees. So 13.48 amperes at an angle of minus 15.4 degrees. So this is the primary current I1. So I hope now you understood how we have solved it. So we have added these two. So by adding these two, I got some current I1, which is minus 13 point some degrees, minus 15 degrees behind that. So this is the, so as many coils are there, that many the equivalent currents will come up in the primary side, and it is just adding everything vectorially to finally know the current. So I hope you understood something from this problem. Now before I leave this problem, uh, I'll tell you that there is another shortcut way of answering this. So let's do the shortcut way of answering this. So I'll open a new file. I'll show you the shortcut way of answering this, and hopefully it will give me the correct answer. So I'll just first copy this question. And then I paste it here. So another way of solving it. So think of it as some kind of a black box. Okay. So I simplify this diagram and then just simply say some electrical box. Let me call it E box. I don't know what it is. There is one input and two outputs for these boxes. So one of the output is 800 watts at 0.8 power factor. Another output is 500 watts. So this is power factor lag. And another output is 500 watts at zero point 0.9 power factor lead. Therefore, just by looking at the powers, so I should know what should be the input power here. So P in I should be able to know. So right away I can tell the active power input will be 800 watts plus 500 watts, that is 1300 watts anyway I know. But what is the reactive power is what we have to find out. And once I know, then I know what is the input power. And if because I know the V1 is 100 volts given, so from this I can actually calculate the I1. So let's do that. So this is S2, this is S3, and this is, we'll need to find out S1. So what is Q2? The reactive power demand of this. So 0.8 is the power factor. So uh, so 800 is active power. So if you divide by cos of power factor, that is 0.8, I'll get the total, I'll get the kVA or the apparent power, and then multiplied by sine of cos inverse of 0.8. If I do this, then I'll directly get the Q2. And because this is lagging, I'll consider Q2 as the power demand. I'll consider it as a positive Q2. Similarly, Q3 will be 500 divided by zero point 0.9 multiplied by sine of cos inverse of 0.9. If I know, then I'll know what is the reactive power supplied by the Q3. So let's do these calculations quickly. So see here, 800 divided by 0.8, this is multiplied by sine of cos inverse of 0.8. So I'm getting 600 watts. So the load connected at terminal 2 requires 600 watts. What about the watts requirement of Q3? So here this is 500 and this is 0.9 and this is 0.9. So 242.16 or minus 242 watts. So the balance watts, so this particular S3 is supplying that many watts to S2. 242 watts is already supplied to this one. So remaining watts that is required, so required watts from winding 1 will be the balance of this. So 600 minus 242. So I get 358 watts are required. So therefore, I know what is my P1. Sorry, S1. S1 will be 1300 plus J 358. This much of watts I require. And I know V1. V1 will be 100 volts. And this is volt amperes. So therefore, What is I1? So I1 is nothing but S1 conjugate divided by V1 conjugate. We had seen this many times, this simple uh, complex power law. So 1300 plus J358 conjugate divided by 100 conjugate. So 100 itself is a reference, so it is, so that is so 13, and here this divided by 100 minus J 3.58 amperes. So this is my I1 current. And if you refer to, so 13 minus J 3.58 amperes, so this minus is coming because of this conjugate, and 3.58 by 100 is, sorry, 358 by 100 is 3.58. This if you remember, if I go back to my earlier answer, after all these calculations, so finally my I1 was coming this 13.58 like this. So exactly the answer is matching. 13 minus J 13.58 exactly is matching with what I got here. So therefore, if I now convert it, I'll be getting exactly what it is here. That is 13.48 minus 15.4. So let me write it here. 13.48 minus 15.4 amperes. So this is the second way of finding your solution. So treating it as a black box, even though I don't know how the what is there inside, how what is the working principle of this black box, I don't know. Just by applying my knowledge of conservation of power, so the input power should match the output power. Unless if there is some storage inside going on for long term, then I cannot apply this. But then I can just see 800 watts is coming out here, 500 watts is coming out here. So therefore, total 1300 watts should enter. So that solves the active power problem. Coming to reactive power, I just using these two informations, I can find what is the reactive power demand here. And since this is lagging and this leading, I have to be careful with the plus minus sign. And net reactive demand I know, and then from that I can just find out this one. So I request you to once again look at this example 18, study it and understand it, and I hope you learn something from this. So this is a short session about some advanced problems. I think we'll take up more concepts in the next lecture. Thank you.